In this chapter, we will be studying quadratic functions. In this lesson, we're going to use what we've learned in previous lessons to solve word problems that ask us to find the maximum or minimum value of a variable.
Okay, well, now that we've taken a look at how to complete the square in a previous lesson here, we learned how to convert from the standard form to the vertex form. Let's think about why that would be significant, okay? Because let's say if you got a parabola that opens like this, or even a parabola that opens like this, okay? Then finding that point is actually quite important, because that point right there, that gives us in this particular situation here, that gives us the minimum value of whatever relationship this is modeling. Right here, this point right here gives us the maximum value of whatever situation this thing is modeling right here. And being able to find those maximum and minimum values is actually a really important skill, and it's something that's going to be exploited quite a bit when you get to calculus here. For right now, we're just going to take a look at just a kind of a specific little set of questions here that we're going to look at that can actually be modeled quite easily with a quadratic. Okay, so we're going to look at number relationships, area and perimeter problems, revenues, this is a big one here, and then projectiles. So what we're going to do here is we're going to read through a scenario here. We want to come up with a quadratic equation, and you know what? Usually this is the hard part right here, is the translation from the written kind of words to the mathematics, to the symbolism of the mathematics here, and that can be quite difficult. And I get that. I don't want to downplay that. If there are people out there that really struggle with that, I get it. Okay, I totally get it. Typically, though, when we do that, we're gonna get it in a form that we can quickly convert into and easily convert into the standard form. But that's not going to be the most useful form of the equation. The more useful form is going to be the vertex form. So we're going to have to complete the square. And then typically we're going to get asked one of these two things. We're either going to get asked for the x coordinate of the vertex, or we're going to get asked for the y coordinate of the vertex. Okay? So actually, the best thing to do here would just be to start jumping in. Let's just start doing some questions. All right, well, we're going to start by looking at number relationships and then problems involving area and perimeter here. Okay? So here we go. We're just going to jump in here. So the sum of two numbers is 50. The sum of their squares is a minimum. Find the numbers. Okay. Now, one of the things that you really want to get comfortable with here, and there's so many people kind of refuse to do this, even though I show everybody, I talk about this with everybody here. You want to introduce or start this problem with a let statement. Okay, you need to identify what your variables are, and this is particularly important in this chapter at this time. We are going to run into a problem very soon, where if you don't take the time to identify what your variables are, eventually when you get to the end of the or near the end of the problem, you're going to look at your answer and you're going to be really tempted to grab the wrong number, because the value of the variable isn't the actual number that you are looking for, if that makes sense. We'll show you that in a bit here. But all that to say, please make sure you identify the variables here. So we'd have the sum of two numbers is 50. I don't know what the two numbers are. So let's just say x is going to be our first number. And then we're going to let y be maybe our second, and I could say larger number, but we're going to say our second number here. Whatever. I just need to have some idea what my two variables are. Now, usually, sentences become equations. Okay? Usually. That is not always the case, but often it is. And in this particular case, it actually is. The sum of two numbers is 50. The sum of two numbers is, okay? Now, almost any time you run into what we call a state of being verb, is, are, was, am, be, that sort of thing, whatever. That's going to be translated over into an equal sign. Okay? So x plus y, the sum of two numbers is 50. Okay? The sum of their squares, okay, so that's just going to be x squared, y squared, is, well, now this is an interesting thing to say here, is a minimum. I'm not telling you what it is. Okay? I don't know what it is. So I almost need to introduce another variable here. Let's call this, well, we'll call it m right here. And I'm going to let this be the sum of their squares. Okay, so I've actually got 3 variables here. Now I've only got 2 equations, but 3 variables here. I don't particularly like that. Okay, there's not enough information here. But because I'm not looking to specifically, like say, solve for everything, what I'm looking for is a specific point in their relationship, that minimum point here. This is what we're going to do. We're going to take equation 1 to start off with. We're going to solve for one of those variables. We're going to get rid of one of them in a second here. And you know what? 9 times out of 10 when I ask students which variable they want to get rid of, it's always the y they want to get rid of. So let's just do that. So I'm going to bring the x over. Now I could have written that as 50 minus x, but you know what? It looks better to have the x up front. I'd prefer it if it didn't have a negative there, but what are you going to do? Okay, but it usually looks better if the x is up front. Then what we're going to do is we're going to take that equation 1 that I just figured out here, and I'm going to substitute that into equation 2 to get x squared plus, well now this is what y was, so this is going to end up being negative x plus 50 squared. Now it's got to be the whole thing squared, because remember y is equal to this whole thing, not just parts of it, the whole thing. So that's why you probably want to put parentheses around that and throw a square up top there. So that's the whole thing squared. And this is going to equal, sorry, not equal 50. Sorry, I just quickly glanced over there. It's going to equal m. Now, I tell you what I'll do here. I know that there's going to be a whole bunch of people out there that when they walk through this, they're not going to like the way this looks. It doesn't matter. But because I know this is an issue for some people, I tell you what, I'm going to swap this equation around. Okay, so I'm going to make this m is equal to x squared plus negative x plus 50 all squared. It doesn't make a difference, but I know some people really prefer it to look like that. Okay, whatever, so what? So now, m is going to equal x squared plus, now I have to square the binomial. If you're not careful, this is where we're going to catch people. Oh, we catch people all the time here. Because, and maybe I'll do this over here, okay? If I've got negative x plus 50 squared, that's negative x plus 50 times negative x plus 50. When you expand that out, negative x times negative x is positive x squared. Whoops. Negative x times 50 is negative 50x. 50 times negative x is negative 50x. 50 times 50 is going to be 2,500. Now, those two terms there combine to get us negative 100x. That middle term is what oftentimes people forget. They just distribute that to both the first term and the last term. You cannot do that if there's a binomial here or larger. It just doesn't do that. If it's a monomial here, then yeah, you can distribute it to each factor. But exponents do not distribute over addition and subtraction. They just don't. Okay? So now if you know deep in your soul that you're the type of person who would just automatically square both of those, and you've got to be very diligent here. Don't listen to your gut. Your gut is lying to you. Write it out. Take a couple extra steps here to do this. This is going to get me x squared minus 100x plus 2,500. So m is going to equal 2x squared minus 100x plus 2,500. Now what I'm going to do here is I'm going to complete the square. Now I'm kind of running out of room. I wrote kind of big here. But I'm going to come up here. I'm going to complete the square on that. And remember how I do that. The first thing I'm going to do is I'm going to move that 2,500 out of the way. I don't need it. Okay? It's not part of my work here. I don't need it. So I'm going to be left with the 2x squared minus 100x. Actually, maybe I'll write a little smaller here. So I'll zoom in a little bit more. Now I'm going to factor the 2 out of those first two terms, because I want, remember, I want the leading coefficient of the x squared there inside the brackets. I want that to be 1. Now, I know that middle term has got to have a factor of 2 in there, and that's going to leave me with 25x. Okay, now, and we've done this before, this tells me that 2 steps down, this is going to be 2 times x, steal that sign, minus 25 squared. And it's what's coming on, happening out here that I don't particularly know what's going on. So that's okay. What I'm going to do here is figure that out here. So I know that I'm going to take that 25 and I'm going to square it, and I'm going to add 625, and then I'll subtract 625 from, well, inside the parentheses there. Now, in my next step here, I'm going to take that negative out because when I complete the square, when I do that little bit of factoring there, I know that those three terms become this binomial squared. And I don't need that negative 25, so I'm going to take it out. And I do that by multiplying by that leading coefficient of 2. So 2 times that negative 625 is going to be negative 1250 plus 2500. Okay, and then I'm going to add those two together, and it's actually going to be really nice. It's going to give me positive 1250, and there we go. So I know that my vertex here is the point 25, 1250. Now it's important to understand what these two variables are. Okay, before you jump on this and say, wait a minute, what do you mean, what are they? This is x, this is y, I'm done. Actually, that's not true, not in this particular case here, because remember what I did? I got rid of y. In fact, I stopped writing the m here, and I should have kept going with it. Now I'm going to put that back in. So that, bear in mind, if I've got, I'll maybe write this up here, if I've got a parabola that looks like this, y equals, I should have put the a there first, x minus p squared plus q, my vertex is p comma q, and that corresponds to x and y. But that corresponds to this variable right there, and then the q corresponds to whatever dependent variable we've got hanging out over here. In this case, I changed that for an m. So what I've actually found here is this is the value of x, okay? So x is equal to 25. The minimum sum of their squares is 1250. That is the minimum that they were suggesting existed here. But this doesn't tell me what the two numbers are. All I know is the one number from that. Oh, if only I had some way of figuring out what the other number was. Oh yeah, right there. I had come up with an equation for y. Y is equal to negative x plus 50. Now, plug the 25 in there. Negative 25 plus 50, 25. So my two numbers here are 25 and 25. So my values are 25 and 25. Good. All right, let's take a look at another one. Zoom out a little bit. So this one says here, we're going to find two numbers whose difference is 8 and whose product is a minimum. Okay, so here we go. So we're going to let x be our first number. There's no real relationship given right now. Actually, sorry, I shouldn't say that. I should not say that. Find two numbers whose difference is 8. Okay, if their difference is 8, then there is a size difference here that I'm going to exploit. I'm going to let x be the smaller number, and I'm going to let y be the larger number here. Okay, and so now when I say the difference between them is 8, what I mean by that is the larger number minus the smaller number is going to equal 8. So there's my first equation right there. Now, and bear in mind how this works here. Bear in mind, although I don't have two sentences here, that and is kind of breaking this up here. Two numbers whose difference is 8 equals 8, whose product is a minimum. Okay, so the product, xy, is going to equal the minimum. So I don't know what that is. I don't know what number is supposed to go there, so I'm going to let m be the minimum product. Just put an m there. Okay. Now, just like in the previous question, I've got too many variables there. So I'm going to get rid of one of them, and as usual, I'm probably going to go back up to my first equation and get rid of y. Because I'm being asked to find the minimum or the maximum, whatever, that's the equation that you complete the square on. Okay, in the previous question, it was this x squared plus y squared is the minimum. That's what I completed the square on. So here it's this product I'm going to complete the square on. So I'll take that first equation, solve for x, and get y is equal to x plus 8. Okay? Now, I will take that and plug that into the second equation. So x multiplied by x plus 8 in parentheses, because the whole thing is representative of 8. Okay, so if x is multiplied by y, it's multiplied by everything that y is equal to. And this is going to be some sort of a minimum. And again, because I know there's going to be people who don't like the way I wrote that, I will change the order. Okay? I watched one student once, she got really angry at me when I wrote it the other way. Whatever. So now up here, I know that my m here is going to be x squared plus 8x. Okay, good. Now I'm going to complete the square on this. And I would start that by moving the constant term over. But in this case, this is great. There is no constant term. I've only got my quadratic and my linear terms. That's all I needed. So I'm good. I don't even have to worry about that step. I also don't have to worry about factoring out the leading coefficient. It's 1. This is a great question. So now I just have to worry about this second bit of this second term here, taking out the 2, which leaves me with 4x. So I know that down here, this is going to end up being x plus 4 squared. I just got to figure out what this final value is. So I'm going to take that 4, I'm going to square it, I'm going to add 16, and I'm going to subtract 16 immediately. And then really in this next step here, I almost don't really need to do this, but just to be consistent, I take the negative term outside the parentheses. In this case, it didn't take me any work at all to do that because the leading coefficient here is 1. And then I'm going to subtract the 16. Okay, whoops, sorry about that. All right, so now my vertex is going to be the point -4, whoops, comma -16. Okay, -16. Now, what are the variables for my vertex here? X is right here, coincides with that value right there. But this isn't the y coordinate, it's the m coordinate. This right here is the minimum product. Okay? Now, I know one of the numbers is -4. That's easy. I know that m in this case, the minimum product that I was looking for, is going to be this -16. That's the value of that. So I got to find y here. But bear in mind, oops, sorry, you can't see m. But I have an expression for y. It's x plus 8. So if x is equal to -4, x plus 8 is going to be +4. So therefore, the two numbers are 4 and -4. Okay, now let's take a look at some area and perimeter problems here. So the first question says a rectangular lot is bounded on one side by a river. Okay, there we go. And on the other side, 3 sides by a total of 80 meters of fencing. Okay, 80 meters of fencing. That's an important bit of information there. We want to find the dimensions of the largest possible lot. So what we're going to try to maximize, we want to maximize area, largest possible lot. Okay? Now, this is a really common sort of problem here, to have one side of the rectangular area blocked off by something. Okay, sometimes it's against a river, sometimes against a barn, sometimes against just a random wall someplace. Whatever, it doesn't really matter, but frequently this happens here. So just take a quick look at this, the way this has been labeled here. I've got width, length, width here. Now, but I know that there's only a total of 80 meters of fencing, which means, therefore, 2 widths plus 1 length has got to equal 80. Okay, so it has to do with the available perimeter there to put the fencing around. And by the way, the diagram here is functioning as my let statement. I know that W is my width, I know that L is my length here. Now, the thing that I want to maximize is the area. So area is going to equal length times width. So this is the thing that I'm going to complete the square on. So here's equation 1, here's equation 2. Again, I got one too many variables, so I'm going to get rid of one of them. And when I look at this right here, between W and L, I'm just kind of lazy here, so I'm just going to choose to solve for the L, because it's just going to take a little bit less work to do. So equation 1 is going to become L is equal to -2W plus 80. I'm just going to bring that 2W term over to the other side. Now I'm going to take this new value, or this new expression for equation 1, I'm going to substitute that into my area equation. So area is going to equal -2W plus 80, all in parentheses, times W, because remember, that W is being multiplied by L. Okay, all of L, whatever L represents, that's what I'm multiplying W by. Now distribute the W through the two terms here in this binomial. I can do that because multiplication does distribute over addition. But okay, remember what we looked at earlier, An exponent doesn't, but multiplication does. So negative 2w squared plus 80w. Okay, good. So here we go. There's an expression for our area in terms of width. Now, I'm going to complete the square in this. Now, one of the first things I would normally do is move that constant term over, but again, there's no constant term here, which is great. It makes things that much easier here. So my area is going to be negative 2w squared plus 80w. I don't need to worry about bringing the constant over, so I'm just going to go to this term right here. Oh, sorry. I forgot to take out the leading coefficient. Wow, I had just done that completely wrong here. The very first thing I need to do is take out that negative 2. That's going to leave me with w squared minus 40w. Okay, minus 40w. Just make sure that you're dividing that negative 2 out of that second term as well here. Now I look at that second term. I know there's supposed to be a 2 there, which would leave me with 20w. And I know from that 2 steps down, this is going to be negative 2 times w minus 20 squared. And it's that value outside there that I need to look for. Okay, so now I come back up here. I know I yanked that number 20 out, so I'm going to square that. So that'll be 400 minus 400. I only need the first 3 terms to get it down to that binomial squared. So I'm going to take the negative 400 out. And I do that by multiplying by that leading coefficient. So negative 2 times negative 400, which means I'm actually going to take out of that a positive 800. And so this will become positive 800 here. So now my vertex is going to be the value, or the point 20 comma 800. Now here, once again, we really want to be careful about what these two numbers represent here. 20 is the W, 800 is the A. Okay? So I know right now that the maximum area that I'm going to get for this, the max area, is going to be 800 meters squared. The dimensions, okay, of this largest area here, well, are going to be 20. Okay, now, let's just think about this. 20, if I knew what W was, I need an expression for L. Well, here we go. And if I plug 20 in for this, negative 2 times 20 would be negative 40 plus 80. Oh, okay, there we go. 20 meters by 40 meters. And those are the dimensions that we're looking for. Okay, let's take a look at another one. I'll zoom out a little bit here. Okay, a rectangular pen is divided into 3 separate pens by placing 2 extra fences parallel to one side. So these two lines here are parallel to the outside sides there. We want you to see this one with the diagram here because it often shows up on assessments without the diagram. Okay, and this, again, this takes the level of this question up a little bit because it's about reading the question and pulling out the diagram from the description. And that can be hard, but that's something that we want you to be able to do. Okay, so I'm going to draw this out here. I just want you to recognize what this means here. One rectangular pen divided into 3 separate pens using 2 extra fences parallel to one side. Now we could have gone this way. It really doesn't matter in this case. So if 600 meters of fencing is available, find the dimensions of the largest area that can be enclosed. Okay, so we got to throw down some variables here. Now, there are at least a couple of different ways of doing this. Okay? So let's kind of zoom in on this a little bit here. I'm going to call this dimension here the width. Hold on. Just going to clean up that little mess I made there with that W. And now, I could do this one of 2 ways. I could either make this distance right here my length, in which case there would be like 3 of them along here. But I don't typically like doing that. I'm going to make this whole thing my length. Okay? I just find that a little bit easier to work with. So now, think about where all the fencing is going. I'm going to have 2 lengths. And how many widths? Well, here, 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 and here. 4 widths. And altogether, that's going to amount to that 600 meters of fencing. Okay? Now, that's going to be my equation 1. My equation 2, because I'm looking to maximize the area, well, area is going to equal length times width. Okay, L times W. And this is what I'm going to complete the square on. So I'm going to end up taking this equation and plugging it into this one. So, let's take a look at equation 1. Whoops. Wow, I can't believe I just did that. I said equation 1, I wrote 2. That's so odd. Okay, so equation 1, we're going to manipulate a little bit. I'm going to solve for one of those variables. Now, look at this right here. 2, 4, 600. I can divide everything through here by 2 to get L plus 2W equals 300. Okay, that's not like a huge improvement, but it does make things a little bit easier. And then I'm going to solve for L because that way I don't have to divide by 2. So L is going to equal negative 2W plus 300. It doesn't matter which variable I solve for, by the way. So I'm just going to choose the one that requires the least amount of work. All right, now we're going to substitute the area equation. So area is going to equal the length, so negative 2W plus 300 times W. Okay, and again parentheses because the width is being multiplied by the length, the entire expression for the length. And now because this is a binomial multiplied by a monomial, I could distribute that monomial through. And area will equal negative 2W squared plus 300W. All right, now I've got this nice expression for area in terms of just one variable. It's exactly what I wanted. Now I'm going to complete the square to find the vertex. Well, move over the constant. There is none. Take out the leading coefficient. Okay, there is one right there. And W squared, this is going to be, minus, okay, because a positive divided by a negative is going to be negative. 150W. And I don't have to do anything else there, so I'm going to now take the 2 out of here, which is going to get me 75 inside there. Okay, now as soon as I know that, okay, as soon as I know that that's got to be 75 here again, and I know I've done this a bunch of times, I already now know 2 steps down that this is going to be negative 2 W minus 75 squared. I already know that that's where that's going. So I got to figure out what's going on out here. So I go back up here and I'm going to take that 75, I'm going to square it. Actually, I'm going to run out of room here. This is going to end up being positive 5,625 minus 5,625. Add and subtract. Again, I only need those 3 terms to get it down to here, so I can move that, whoops, you can't even see that. I can move the negative 1 out, so I'm going to multiply that by my 2, because remember, that's how I get things out of the parentheses. I got to multiply by the coefficient. 625. And when you multiply by 2, we're going to get 11,250. So out here, I get 11,250. My vertex is then going to be 75, comma, 11,250. What does that mean? Well, it means based on my variables here, that means my width. Okay, therefore my dimensions here, my width is going to be 75 meters. Okay, I grab that right out of the equation. W, and I know that's going to have a max area. Maximum area is going to be 11,250 meters squared. Okay, that's what I'm reading right out of the equation. Now, what I don't have right in front of me is an expression for the length. That's why I come over here. The length is going to be equal to negative 2W plus 300. Now, will an expression like this always exist? Well, almost always, yeah. Yeah, based on the way we're going to start these problems here, yeah, you can almost always expect to see something like that. So down here, if I plugged 75 in, that's going to get me 150 meters for the length. And so there you go. The question was asking for those dimensions. All right, let's do one more. Back up a little bit here. So in this question we read that a rectangular field is enclosed with 920 meters of fencing. Determine the dimensions of the largest field that can be enclosed. Okay. So here we're going to just draw this rectangle. Now no diagram is provided. I gotta provide this for myself here. I'll just call this width, I'll call this length. I'm not given any indication of whether there's anything else going on there. It just says a rectangular field is enclosed, so that's it. But because it's a rectangular field, I know that this would also be W and this would also be L. So I know that 2 W's plus 2 L's is going to equal 920 meters of fencing. Okay? Now, what I'm looking to do with this is find the largest field that can be enclosed. So I'm going to maximize the area. So area will equal length times width. So here's equation 1, here's equation 2. All right, now what I got to do, zoom in a little bit. Now what I'm going to do is I'm going to take that equation 1, and you should notice, man, we've done the exact same thing like over and over again. Okay, it's almost like there's a pattern there. I'm going to simplify this first equation to get W plus L is going to equal 460. And then, you know what? We've done everything up there in terms of W, so let's do the same thing here. So we're going to let L equal negative W plus 460. And now I'm going to substitute that into my area equation. So area is going to equal negative W plus 460 times W. And then I will distribute backwards there to get negative W squared plus 460 W. Good. That's the equation I'm going to complete the square on. Okay, it's a nice, simple little quadratic relationship between the area and the width. Let's come up here. Now I'll rewrite that. So negative W squared plus 460 W. All right, now again, I would move the constant over. It's not there. So now I'm going to take out the leading coefficient. Okay. I divert my attention to what's inside here. So I know there should be a factor of 2 there, which will leave me with 230 W. Okay, that's important there. And I know that 2 steps down, this is going to equal W minus 230 squared. And I'm just going to figure out what the value for Q is going to be. So I take this 230 and I'm going to square it. Now I know I'm going to get a number here that's bigger than the room that I'm given. And when I square that, I'm going to get 52,900, which I subtract immediately. And now I know this is going to be negative W squared minus 460W plus 52,900. And then I'm going to take the negative 1 out by multiplying it by that negative leading coefficient to get positive 52,900. There are no other values back here, so it's just 52,900. So here we go. Our vertex is 230, comma 52,900, meaning that my dimensions, okay, my dimensions are going to be, my width is 230 meters. I know that my max area, okay, is going to equal this 52,900. Okay, the y-coordinate of the vertex here, or I guess the value of the dependent variable is always going to be the thing that you've maximized or minimized. Okay, and then our length here, where do we get the length from? Well, I gotta go look for that expression for length right there. And if I plug in that 230, you'll see that I'm going to get 230. Now, isn't that interesting? Let's just talk about this real quick. My length and my width are the same. So what does that mean about this shape here? If the length and the width of a rectangle are the same, that means it's a square. Now, it turns out that's an interesting relationship. That would have happened no matter what the area was that you threw in there. Okay? If you want to find, if all you're doing is just throwing down this kind of a rectangular shape here, and I'm asking to maximize the area, that will always happen if the shape that it takes is a square. Yeah, it's kind of neat.